Today we're diving into diffusion models. Traditionally, improving image quality at inference time meant simply adding more denoising steps. And sure, that helps, until it doesn't. Eventually, the improvements hit a plateau, but this research changes the game. Instead of just piling on denoising steps, it's all about finding the perfect noise to work with. It dives into powerful new methods, exploring verifier types like oracle, supervised, and self-supervised, and advanced search algorithms to identify better noise. These techniques not only improve quality, but also open the door to more efficient inference. Now let's jump in and see how this noise hunting journey works.
You know how generative models have made huge strides lately, right? They've gotten really good at creating realistic images, texts, and even audio. A lot of this success comes from scaling, using more data, bigger models, and more computational power during training. But here's the thing. While scaling during training is well understood, scaling during inference, when the model is actually generating stuff, is a bit trickier, especially for diffusion models. Diffusion models work by starting with pure noise and gradually refining it into something meaningful, like an image. The number of steps they take to do this is called denoising steps. More steps usually mean better quality, but there's a catch. After a certain point, adding more steps doesn't help much. The performance plateaus. So this paper asks, what if we could scale performance in a smarter way during inference, without just adding more denoising steps? The authors frame this as a search problem change. Instead of just cranking up the number of steps, they look for better noise inputs to start with. They explore two main ideas: using verifiers to give feedback and algorithms to optimize noise candidates. And guess what? Their experiments show that this approach actually works. Scaling inference time computation this way leads to better outputs. Let's unpack how they did it. Carrying on, we know generative models have transformed fields like language, vision, and even biology. Their success often links back to these scaling laws. More data, bigger models, and more compute during training generally lead to better performance. With large language models, recent research has made it clear that even after training, we can squeeze out more quality by spending more computation at inference. This helps generate more fluent or context-aware outputs. Diffusion models work by removing noise across several steps to produce a final sample, be it an image, audio clip, or video segment. They allow a degree of flexibility at inference time because we can tweak the number of denoising steps. More steps often yield better quality but cost more compute. Traditionally, if performance gains flatten beyond a certain point, researchers try to minimize these steps for faster inference. But here, we explore the opposite. How can we use extra inference compute more effectively? Perhaps by guiding or searching for better noise configurations. This is what sets the stage for the rest of our discussion. Let's look at Figure 1 to see how scaling inference affects performance in diffusion models. You'll notice two approaches: simply increasing denoising steps, shown with a dotted line, versus a search-based method that optimizes the noise inputs, shown with a solid line. On the x-axis, you have the amount of computational effort, often called the number of function evaluations, or NFE. On the y-axis, you'll find various quality metrics like Fréchet inception distance, or FID, inception score, or IS, clip score, which measures how semantically aligned images are with prompts, and aesthetic scores. What jumps out? While more denoising steps improve performance at first, the improvements quickly level off. The search-based approach, on the other hand, keeps climbing as we allocate more compute. This suggests that searching for better noise inputs is a more effective way to spend our extra resources than simply cranking up denoising steps. In short, if you want to push diffusion model performance further, strategic noise optimization is key. So why does just adding more denoising steps eventually hit a wall? Diffusion models indeed get better results initially when you use more steps, but the returns dwindle beyond a certain threshold. That's why most research focuses on fewer steps for efficiency. But here, we're flipping that perspective. Let's see how to make the most of scaling compute during inference rather than just shrinking it. The critical insight is that diffusion models start with random noise, and some noise seeds will naturally produce better samples than others. The paper frames this as a search problem for optimal noise seeds, rather than blindly increasing NFEs. To do that, the authors define two important ingredients: verifiers, which score the outputs, and algorithms that explore different noise configurations. By pairing the right verifiers with effective search algorithms, it's possible to more efficiently spend our compute budget to boost quality beyond the typical plateau. Now let's talk about the design framework for scaling diffusion inference. The study introduces three main search strategies. Selecting from a fixed candidate set. Evaluate multiple noise samples and pick the best one. Zero-order search. Iteratively refine noise candidates using feedback search over paths. Extend this refinement to entire sampling trajectories, not just single noise inputs. They start by testing these ideas on a simpler task, class-conditioned image generation on ImageNet, where the evaluation is straightforward with metrics like FID and IS. Then, they apply the same framework to text-conditioned tasks. Text prompts are more complicated, so the verifiers need to be more sophisticated. Multiple verifiers are used to check for biases and see how each aligns with the task. An ensemble of verifiers often works better, as it captures different aspects of sample quality and avoids overfitting to any single viewpoint. Ultimately, these experiments show that a search-based approach can outperform traditional denoising alone. They also highlight which verifier algorithm combinations work best for different goals. Before diving deeper, let's remind ourselves how diffusion models work. Essentially, we have a forward process that adds Gaussian noise to clean data in incremental steps, until you're left with pure noise. The reverse process, denoising, tries to reconstruct the original data step by step. Mathematically, it can be framed as solving differential equations, ordinary or stochastic, that guide how we reduce noise. During training, the model learns a score function to estimate how likely the clean data is at each noise level. Armed with this knowledge, the model can effectively reverse the noise process and generate coherent samples. That's why it's crucial to figure out the best noise patterns at inference, since the model is basically a noise-to-data converter. Let's look at Figure 2 to see how these three search methods refine sampling in diffusion models. Random search. You generate a bunch of noise samples, evaluate them, and pick the best one. Zero-order search. You go a step further by exploring nearby noise variants around your best candidate, using feedback to refine it across iterations. Search over paths. You don't just look at the initial noise, you consider entire sampling trajectories and refine them for even better results. Diffusion models let you scale compute at inference because they're inherently flexible. Each noise level can be considered a kind of submodel, giving you a lot of opportunities to optimize. By searching at various noise levels, you can spend your extra compute in a more strategic way than just running more denoising steps from a single noise seed. This part emphasizes that randomness in diffusion models, especially in the noise we inject, significantly impacts final outputs. Instead of treating that noise as a black box, the paper proposes turning inference into a search problem. How can we identify the best noise seeds? Two axes form the backbone of this approach. Verifiers. Pre-trained models that evaluate or score generated samples. Algorithms. Procedures that use verifier feedback to find the best noise seeds. This structure lays the groundwork for using inference-time resources more efficiently. By picking the right verifier to match your goal, image realism, semantic alignment, etc., and the right algorithm, random sampling, zero-order refinement, or path exploration, you can tailor your search to maximize the impact of your computational budget. Next up, the paper describes algorithms that take feedback from verifiers to guide which noise samples to pick. Any given algorithm needs to connect the verifier's scores, the diffusion model itself, and the candidate outputs. The cost here, search cost, is basically how many forward passes we make through the model to find a good noise seed. To illustrate, the authors first show a class-conditional ImageNet generation example. They demonstrate that you can split your compute between the number of denoising steps and the search cost. The simplest method mentioned is random search. You just sample multiple Gaussian noise vectors, run them through the model, and pick whichever output the verifier scores highest. This is sometimes called a best-of-n strategy. Straightforward, but already surprisingly effective. They then discuss evaluating those noise candidates with an oracle verifier, which knows the final evaluation metrics, like FID and IS for ImageNet. If you could directly score your samples using ground truth, random search gives significant gains if you're willing to invest more compute. The results in Figure 3 show that as you increase the number of samples you test, FID goes down and IS goes up. Of course, real-world scenarios don't usually let you peek at the ground truth. That's why the paper introduces supervised verifiers, which measure sample quality and condition alignment using pre-trained classifiers. These are more practical, but also more limited, since they rely on information that might not perfectly match the final evaluation. Still, they're a good proxy for guiding the search when you don't have an oracle. Now, if you check out Figure 3, you'll see exactly how the oracle verifiers push FID down and IS up with more inference compute. Different classifier-free guidance weights, like 1.0 versus 1.35, also affect performance trends. Everything looks great with an oracle, but we can't rely on that in real settings. So the authors bring in Clip and Dino as supervised verifiers. These models do classification or embedding-based assessments, using learned knowledge from large-scale pre-training. They see if samples align well with given labels, trying to replace the oracle's all-knowing viewpoint. Check out Figure 4 for how Clip Zero Shot and Dino linear head verifiers perform at different guidance weights. Both can improve inception score over baseline, but, interestingly, they focus on individual sample quality and may ignore diversity. If a verifier only cares about a single measure of quality, you can get mode collapse, where your generation focuses on a narrow set of outputs that the verifier loves. The paper calls this verifier hacking, akin to reward hacking in reinforcement learning. Random search can exacerbate this by repeatedly sampling from the same style of noise once it finds a sweet spot for the verifier's preference. Then we move on to self-supervised verifiers. Look at Figure 5 to see how Dino and Clip outputs correlate well with each other in their feature spaces. By leveraging this feature space similarity, we can build verifiers that don't need extra condition labels, which can be useful in areas like medical imaging. The experiments show these self-supervised verifiers can scale similarly well under classifier-free guidance, though future work is needed to expand their utility in more real-world scenarios. To handle the issue of overfitting in random search, zero-order search is introduced. This technique starts from a random noise seed and looks at nearby samples in neighborhoods to see if they yield better outputs. The best sample becomes the new pivot for the next iteration, and so on. It's called zero-order because it doesn't require explicit gradients. It just checks which direction in noise space gives better results, purely from repeated evaluations. It's more efficient than a first-order approach, which would need backprop through the entire diffusion sampler. The trade-off is how many cycles of searching you can afford and how wide a neighborhood you check each time. Comparing zero-order search and search over paths is the next step. Figure 6 illustrates how these methods influence FID and IS as we spend more compute. While first-order gradient-based methods are conceptually possible, their high cost often outweighs their benefits. The neat thing about diffusion sampling is that it's iterative, so you can try creative algorithms that refine noise at intermediate steps. This is basically search over paths and rives. You branch out from initial noise states, refine them across multiple levels, and eventually pick the best trajectory. You get more flexibility without ballooning compute too much, making it practical for larger models. So these scaling algorithms, zero-order search and search over paths, both aim to optimize noise selection for better outputs. Zero-order focuses on local refinement, while search over paths broadens the search to intermediate sampling steps. Figure 6 shows they can correct the diversity issues we saw before. A smaller neighborhood size in zero-order search might be more efficient if you have limited compute, while going bigger pays off if you have lots of resources. After discussing these improvements, the paper transitions into text-conditioned image generation, which is more complex because you also have to align with textual inputs. This is where advanced verifiers really shine, given the multifaceted nature of text-to-image tasks. Now the paper shifts to datasets, models, and verifiers for text-to-image systems. Two key datasets come up. Drawbench, 200 prompts covering 11 categories, used to see if models handle tricky textual descriptions. T2 iCompBench, focused on testing attribute binding and object relationships in generated images. They use the FLUX.1 dev model, which is a diffusion-based text-to-image system. For verifiers, they rely on tools like an aesthetic score predictor, clip score, and image reward, each reflecting different aspects: visual appeal, semantic alignment, and overall preference. Image reward attempts to combine aesthetics, alignment, and safety into one metric, making it a more comprehensive measure. The paper notes that self-supervised verifiers aren't as effective in text-to-image tasks, because here we really need to capture whether the output aligns with a given text description. The evaluation strategy includes any verifiers not used in the actual search, plus large language model, LLM, based evaluators that can grade images on multiple dimensions. The Gemini 1.5 model, for instance, scores outputs based on criteria like prompt accuracy, creativity, and emotional resonance, then averages them for an overall grade. This approach introduces a more nuanced, human-like perspective that goes beyond simple classifiers. The upper half showcases how scaling compute impacts the outputs of models like CIT-XL and PixArt-Sigma. For the CIT-XL examples, notice the gradual refinement in visual details, such as the sharpness of a lighthouse or the glassy clarity of an hourglass, when increasing denoising steps. However, when compute is allocated to search-based methods instead, the outputs diverge into more imaginative variations, such as entirely new color schemes or lighting effects. Next, the PixArt-Sigma model brings a more artistic twist to prompts like a saxophonist. Denoising brings precision to textures and shapes, while search emphasizes stylistic variety, offering new moods and creative interpretations. Together, these examples underline the trade-offs between enhancing detail and expanding creativity, shaped by how compute resources are distributed. The lower half continues the theme of compute trade-offs, using flux1.dev with playful and complex prompts. For instance, a laptop on a teddy bear evolves through denoising steps to display sharper textures and edges, whereas search introduces unique creative choices, like adding unexpected accessories or altering the bear's pose. Similarly, for an athlete cat at a press conference, denoising improves the clarity of fur and facial expressions, while search generates entirely new interpretations. Perhaps the cat is dressed as a business professional in one version or wearing sports gear in another. These examples illustrate how compute allocation lets you prioritize either fine-tuned perfection or diverse creativity. The choice depends on the task's goal, sharpening realism or embracing variety. Next, we explore Figure 8 to see how search methods ramp up performance in flux1.dev. 4 metrics appear: aesthetic score, clip score, image reward, and an LLM-based grader. The chart highlights that image reward sees the biggest boost, perhaps because it's designed to capture multiple aspects of quality and alignment. A verifier ensemble that combines metrics also does well across the board, indicating that mixing feedback signals can yield well-rounded improvements. Finally, we get an introduction to the T2 iComp bench pipeline, which tests how well a model handles compositional tasks, like placing multiple objects in correct spatial or relational arrangements. Tools like BLIP and Unidet break down images into attributes and objects, verifying that each part of the prompt is accurately reflected. The paper then evaluates flux1.dev on the drawbench dataset. They point out that verifiers must match the demands of each prompt. Some prompts focus on aesthetics, others on correctness or conceptual alignment. The LLM grader acts like a stand-in for human judgment, bringing broad, pre-training knowledge to the table. In Figure 9, you see how scaling compute translates into higher scores on various metrics, like aesthetics or text alignment, confirming that a well-designed search strategy can adapt to different tasks in drawbench. Now let's talk about the aesthetic and clip verifiers. They each have their own quirks. Image reward and verifier ensemble usually match human preferences better, especially on tasks like drawbench. Meanwhile, the aesthetic verifier might push the model to generate overly stylized images, losing some textual faithfulness. Clip might stay loyal to the text at the expense of visual polish. These biases can lead to a form of verifier hacking. But the proposed search approach maintains diversity instead of collapsing into a single style or interpretation. In short, you get a more balanced outcome that doesn't cling to a single verifier's bias. Then there's a comparison of how verifiers behave on drawbench versus T2 iComp bench. For T2 iComp bench, accurate relationships, like correct colors or object positions, are crucial. Table 1 breaks down how each verifier does on attributes such as color or texture. The results show that the aesthetic verifier offers negligible improvement here, sometimes even making things worse, while image reward does quite well across multiple aspects. A combined verifier ensemble tries to balance everything, whereas clip again struggles due to not capturing all the nuances people care about. This is a reminder that verifiers have to be chosen carefully, depending on what you want from your generated images. Moving along, the paper shows Table 2, which details how various search algorithms and verifiers score on Drawbench. Algorithms include random search, zero-order search, and search over paths, each tested with verifiers like aesthetic, clip score, image reward, and ensemble. For instance, you might see that image reward plus random search hits the top image reward metric, while the verifier ensemble might shine when evaluated by the LLM grader. Zero order and search over paths often provide more stable improvements since they refine noise iteratively, potentially escaping local optima. The takeaway? It's crucial to match your search algorithm and your verifier to your end goal. Next, the conversation turns to how fine-tuning interacts with these search strategies. The paper highlights a method called Diffusion-DPO, which tweaks the model distribution based on reward functions aligned with human preferences. They measure how well this fine-tuned model performs under metrics like aesthetic score, clip score, and pic score, another measure of human preference. Table 3 shows that fine-tuning does help, but combining it with search methods, like random search, boosts performance even more. So, even if you've done specialized training to align with user feedback, you can still benefit from a final search step to refine your samples at inference. Now let's consider how we budget our compute in an iterative diffusion process. There are two main things to tweak. Number of search iterations. More rounds of searching typically converge on better noise seeds. Compute per iteration, e.g., denoising steps. Using fewer steps means faster iteration but lower quality per round, while more steps cost more but can yield better samples. The paper suggests practical guidelines. Pick a total compute budget and distribute it sensibly between how many times you refine candidates and how many denoising steps you use each time. That way, you can avoid wasting compute where it won't help. In practice, the authors lock in what they call the optimal number of denoising steps. For instance, 250 steps for ImageNet and 30 for text-to-image tasks, based on prior experiments. Figure 10 shows how changing the compute per iteration affects overall performance, and you can see diminishing returns if you overshoot a certain threshold. After covering these details, they compare smaller models like SIT-B and SIT-L for ImageNet or PixArt Sigma for text-to-image against larger ones, measuring how well each scales with compute in terms of flops. This is important for folks who can't train or run giant models but still want good results by using inference cleverly. Sticking with ImageNet, Figure 11 illustrates how models of different sizes scale up with extra compute. The fidelity metric on the left shows smaller models like SIT-B hit a ceiling sooner, while bigger ones like SIT-L and SIT-XL keep improving. The inception score on the right reveals that under certain compute budgets, SIT-L can outperform SIT-XL, suggesting that bigger isn't always better if you only have so much compute to spend. SIT-B lags because its baseline performance is lower, so throwing more compute at it doesn't help as much. This all underscores how your choice of model size and compute scaling strategy really matters. Then, in Table 4, we compare PixArt Sigma and FLUX in terms of compute efficiency. Surprisingly, PixArt Sigma can match FLUX's quality using only a fraction of the compute. If you double PixArt Sigma's inference compute, it can even surpass FLUX. This highlights the importance of focusing on compute scaling at inference. You can potentially save huge training costs by being clever with how you spend compute later on. Turning to related work on test-time compute scaling for large language models, the paper notes that research is exploring better search and planning algorithms, more effective verifiers, and test-time scaling laws. The lesson here is universal. How you allocate compute at inference can dramatically affect results, whether in text or image tasks. After that, the discussion shifts to fine-tuning diffusion models for human alignment. Some methods treat the denoising process as a decision-making problem, applying reinforcement learning to shape the model's outputs based on feedback. Others pass gradients through the sampling process or rework loss functions, to better match what users prefer. These strategies can help ensure the model behaves in line with certain ethical or practical standards. Another dimension is test time sample selection. For instance, you might have a pre-trained metric that compares generated samples to real images, or one that's trained on human feedback. By filtering or ranking samples at inference time, you can pick the best ones even if your base model doesn't perfectly align with the final task. Finally, the paper outlines recent ideas for sampling from good noise distributions, like using transformations or small models to predict which noise seeds are likely to succeed. Although these reduce test time cost, they often need extra dataset preparation or might not generalize well. Overall, the framework here, scaling computation through search, represents a versatile way to push performance. The conclusion is that the effectiveness of inference time scaling depends heavily on the task's verifiers and search algorithms. Different scenarios demand different configurations. The authors also note that many verifiers have biases, so future work should refine them to align with real-world goals. That wraps up this exploration of how to push diffusion models beyond just adding more denoising steps. Thanks for hanging out on a Saturday. Now go enjoy your weekend.